Hello and welcome to Introducing Red Hat OpenShift 4. This is part 1 in the series, which will cover an introduction to Kubernetes. I'm Ryan Jarvinen, a developer advocate on Red Hat's OpenShift team. You can find me online as Ryan J on GitHub, IRC, Twitter, most places. And I've been talking about OpenShift and Kubernetes for quite a while now. For folks that are new to Kubernetes, this is something that has evolved over the years. It kind of started out as a system within Google for managing large collections of containerized processes over arrays of machines. And they had a couple projects internally, one called Borg and then another called Omega, that helped kind of lead the way along this line of tooling for operations professionals and site reliability engineering type folks. And Kubernetes is their kind of third major attempt at this way of managing processes. And at this go, they've worked with the open source community, and Red Hat especially has been a major partner in this effort. And it's been a major leap forward for cluster scale computing. And we'll kind of cover some more details of what Kubernetes offers throughout the initial sections of this presentation. So on a more technical level, Kubernetes is really meant to be an enterprise-grade distributed process scheduler, acting over multiple machines at really kind of a cluster-wide scale. This platform essentially provides declarative controls, basically spec files, which are written either in your choice of JSON or YAML, which make it very easy to manage workloads in an aggregate form. You can manage collections of highly available production quality processes using really efficient tooling and hopefully reduce the amount of code that you have to write over time when dealing with these complicated distributed solutions. One major piece of the Kubernetes soft infrastructure is called the control plane. It's a group of machines, or in Kubernetes terminology, nodes, that are responsible for hosting core platform services. This includes pieces like the Kubernetes API, which offers a control point for managing basic resource types. These resource types allow you to provision new containers and manage your workloads via this simple API. There's also a very nice collection of command line tools. I'll be showing a couple of command line examples as we step through this content. Behind the Kubernetes API is a distributed data store called etcd. etcd is used to keep track of this cluster's state. Depending on the amount of tolerance you want to have for failure in your cluster, you might choose to have more or fewer etcd instances, as well as Kubernetes API instances. 3 or more generally gives you the high availability type of feature, which is generally what Kubernetes is trying to solve for, the ability to provide highly available solutions. And providing a highly available control plane and data store is a critical part of the solution there. etcd was initially developed at CoreOS, which is part of the Red Hat engineering team. Kubernetes includes a set of basic API primitives that we'll interact with. The first 5 terms that we'll cover are node, pod, service, deployment, and replica set. I've already mentioned nodes when talking about the control plane, But more specifically, a node is a host machine, this could be physical or virtual, where your containerized processes are run. Activity on each node is managed by a kubelet process, which receives workload scheduling instructions from the control plane. Pods are a group of one or more co-located containers. If you wanted to launch a pod from the command line, you can run a command like kubectl create-f followed by the name of a local or a remote file in order to launch or provision a new group of containers on the cluster. This is an example of what a minimal pod spec might look like. You might notice a few of the attributes that I outlined in the previous slide. Kind is the type of resource that we're interacting with. API version is the versioned release of this particular API resource. Metadata includes information like creation timestamps, resource ID, and labels that can be used to select groups of objects. And the last two major fields are the spec and the status. Generally, you will set the spec on an API resource, and Kubernetes will do the work to fulfill and report back in the status area. This means that for each API resource, there's almost always two responses. The spec includes the requested resource state, and the status returns the actual resource state as currently known throughout the cluster. Pods will automatically do health checking for process one in each container. This means if the initial process fails, it's very easy for Kubernetes to restart it or restart the group of containers as a unit. Pods are scheduled to be run on nodes, and pods also represent your minimum increment of scale. If you have two web services that need to be scaled independently, they'll always need to be represented as two distinct and separate pods in the Kubernetes API, or two separate deployments, replica sets. We'll get into those topics next. Services are a Kubernetes resource that basically act as an internal load balancer, helping to spread traffic across a collection of pods. To create a new service or load balancer, you can use the kubectl expose command in order to provide access to the containerized workload. To see the results of this operation, try running kubectl get pods or kubectl get services. You can also use label selectors to list pods or delete pods in bulk. This example shows listing and deleting using -l run equals hello-k8s, which is a label selector that will identify all of our pods in the current group and delete those same pods using the same label selector. The last command deletes the service object that contains the ID hello-k8s. A service is basically an internal abstraction for a load balancer. The service resource uses label selectors to discover where traffic should be directed within the cluster. Label selectors can be used to organize workloads and to manage groups of related resources. Deployments are a specific resource type in Kubernetes. This means that the operation of delivering your software is now something that is entirely standardized and designed to help provide zero downtime while updating stateless applications. This kubectl run command example will generate a new deployment spec file. I'm including the --dry run and -o JSON flags in this example in order to output a new deployment spec file to standard out. I'm then redirecting the output into a file called deployment.json. You should be able to type cat deployment.json in order to review the output. This is what you should see in the resulting deployment spec file. As noted before, this resource file starts off with a kind of resource. It's internally typed. It's a versioned resource. In this example, we see it's versioned as apps/v1 beta1. There's a metadata field, including timestamps, resource IDs, and label selectors. And there's also a spec, including a replica count. This is a new attribute that we haven't seen yet. This particular specification attribute allows the collection of pods to quickly be scaled up and down by setting this value. There's another attribute inside the spec called template. This template includes a pod spec within the deployment spec. This pod spec is used whenever new pod resources need to be created on the API. Anytime the deployment spec replica count and the deployment status replica count are out of alignment, Kubernetes will automatically add more pods in order to get the two spec and status values back in alignment. This example shows how to create a new deployment based on the deployment JSON file that we created earlier. Running this operation should create the deployment resource and set its initial spec.replicas value to 1. The next example shows how to use kubectl expose to create a Kubernetes resource that exposes the hello K8s deployment using a node port type service. Including the --dry run and -o JSON flags helps allow this spec file to be outputted to standard out and then stored into a new file named service.json. You can review the service.json file to see what a raw service specification looks like. You can also run kubectl create -f on your resulting service.json file in order to expose the service based on a known specification. Leaving out the dry run and -o JSON flags in the initial command would essentially expose the deployment in a single command instead of creating the spec file as an intermediate step. This just shows you how to generate spec files on your own if you wanted to edit the raw JSON or YAML. Kubernetes and the OC command line tool both allow you to list multiple resources by type if you need to. Now's a good time to use the kubectl or OC get command to attempt to list pods, services, and deployments all in a single command. You can then connect, if you're running Minishift, this following command should allow you to connect to your remote environment and see if it answers. Another really impressive feature of Kubernetes is its ability to quickly scale up replicas of an existing service. This really goes along the lines of helping ensure high availability of your solutions. You can use the kubectl scale command on the deployment resource in order to set a new replication factor. This command should set the replication count and the spec.replicas value to 3. You can list the resulting number of pods to verify that the action has completed successfully. You should see 3 pods in the resulting output. Another great feature of Kubernetes is auto recovery. Kubernetes will automatically watch for changes in the count of pod resources, similar to how you might run this command, kubectl get pods -- watch. Any changes to the active list of pods will automatically be echoed back to you on the command line. In another terminal, we can try deleting several pods by ID in order to see what happens when the spec and status move out of alignment with each other. kubectl delete pod followed by the pod IDs will delete multiple IDs by resource by ID, multiple resources by ID. This full example, if you copy and paste it from the slides, should grab the top 2 pods from your list, or 2 random pods from the list, and delete them. You can run kubectl get pods to see what happened and how many pods remain. The expected result after deleting 2 pods is Kubernetes should automatically notice that the replica spec and the replica and the replica value in the status field are out of alignment. The spec will suddenly say 3 while the status says 1. At that point, Kubernetes will provision 2 new pods on the API in order to fulfill our requested replica spec of 3. Once this is back in alignment, Kubernetes will continue to actively check to make sure any pods that need to be added, restarted, or removed are taken care of and managed effectively. Some other things to note from this section: you can use the dry run flag to generate new resource specifications without performing API operations directly. And Kubernetes uses a declarative style specification for comparing the spec and the status, allowing you to kind of set it and forget it, which hopefully makes a lot of your coding more simple because you can, to some extent, rely on services to be highly available. Replica sets are the last topic we'll cover in this Kubernetes Fundamentals section. A replica set provides replication and lifecycle management for a specific image release. I have a few command line examples shown in this slide here that show how you might use kubectl set image on a deployment resource in order to change the image tag from :latest to :v1. This should perform a 0 downtime rolling update of the deployment resource as long as there are a minimum of 3 available. You can use kubectl get rs to view the rollout as it spins up replicas on an initial replication controller and spins down replicas on the older replication controller. To view the list of previous rollouts, you can use the kubectl rollout history command on the deployment resource that you would like to investigate. And you can roll back by running kubectl rollout undo deployment and deployment ID. Having this standardized software delivery, containerized software delivery completely standardized and included as part of the platform is really, really great to have this solved at a community level. And it's great to have higher level, have this fundamental solution solved in a really elegant way so we can build higher order abstractions by recycling these fundamental primitives on the Kubernetes API. These are all meant to be very low level building blocks that allow higher order distributed solutions to be built on top. And that's really what we're doing with OpenShift. Replica set attributes. Replica sets provide lifecycle management for pod resources. This sounds very similar to what I just described with deployments. The main difference is deployments create replica sets to manage pod replication per rollout or per change in image tag, per change in pod spec, per change in environment variables. Each of these changes on the deployment resource will in turn generate a new replica set, which will generate new pod resources in turn. If we try to delete pod resources first, the replica set will automatically create new pods in order to fulfill its internal specification. And if we delete replica set resources that are active, the deployment resource will automatically recreate any replica sets that go missing, which will in turn recreate the pods. So you really have to kind of delete these things from the top down, starting at the higher order abstractions, which should in turn clean up their lower level abstractions as part of their teardown process. So to summarize, Kubernetes is an operations tool. It provides open source management for collections of processes over groups of machines. What it tries to provide is a very clearly spec'd set of fundamental resources. It really tries to steer clear of solving all the world's problems and all the world's use cases. The Kubernetes documentation actually has a what Kubernetes is not section that clearly calls out Kubernetes is not designed to be an all-inclusive platform as a service style solution. This is very good to know what your scope and what your purpose is as a project, but it also leads to solutions where there's a lot of gaps around the edges, where in order to really be effective with Kubernetes, you're very quickly going to realize you need access to aggregated logging, you need access to metrics, application metrics, you need access to user access management and identity management integration. There's a whole collection of services that go along with helping you be successful using Kubernetes. And Red Hat has been a major player in this landscape, and we've been doing a lot of work to help provide a supported base that you can work from within this large context of this large CNCF and cloud native ecosystem. So what Red Hat does is we provide a distribution known as OpenShift. The actual distro name is codenamed OKD, and we take in upstream bits from Kubernetes, from the OCI container community, from Fedora, from all over the open source space, and try to provide a supported collection of everything you need in order to be fully productive on any hardware. We do this in a variety of ways. Generally, we offer support around OpenShift via a standard mechanism like we do with RHEL, where you get licenses and can get support, first-class enterprise support from Red Hat. I'll get more to the offerings at the end of the slides, but at a very high level, OpenShift really tries to include and extend and be a distribution around Kubernetes in order to help you be more successful and more productive. Same role that we play relative to the Linux kernel. We don't just give you the Linux kernel and say good luck. We also give you command line utilities, your bash login, things like multi-tenant security, package management, the ability to perform in-place upgrades of your operating system, all kinds of nice features that go along with being productive with Kubernetes. So a really full-featured Kubernetes distribution that focuses on high-level features like being able to build, automate, iterate, and collaborate without regard for really the hardware that you're using, other than the performance requirements that your workloads have. This image shows kind of a stack diagram with Red Hat Enterprise Linux at the bottom. That's a fundamental piece of how we put OpenShift together. No other Kubernetes distribution is trying to provide a multi-tenant safe cluster environment. Every other Kubernetes offering I'm aware of has a single tenant per cluster type of model. Red Hat has a lot of customers and enterprise use cases that really expect a multi-tenant safe system, and that's part of what we provide with OpenShift. So in any of our supported offerings, we're going to expect RHEL or Container OS, RHEL Core OS on the host layer, so we can use SE Linux to protect the host instances from the containerized workloads. From there on up, Kubernetes is really the next standardization layer. On top of that, OpenShift also provides additional build automation and developer focused features. The first major feature we'll get to on the OpenShift side is build automation. OpenShift provides easy workflows for building and deploying containerized applications. Web developers can select a item out of the service catalog, so provide their repo information and application name, click Create, and they're off and running with a new application in the cloud. OpenShift will report back build statuses, stream the logs of the build, and return a application URL immediately that can be asked, that can be used to access your application. Once the application is fully deployed and up and running, you can use these arrow keys to scale up or down with a click of your mouse. OpenShift also uses a tool called source to image to combine source repos and operationally maintained builder images to produce the resulting application container images. Source to image is available as a standalone project for use with Jenkins or other externalized build systems. OpenShift provides git push to deploy style automation in the application configuration section. This particular application shows a configuration page with a generic webhook URL and a GitHub webhook URL. These webhook URLs can be pasted into your GitHub Enterprise, GitHub, GitLab, Bitbucket. Most modern revision control systems will have support for a webhook integration that allows your revision control system to call OpenShift and notify it when new code has arrived. This allows a full continuous delivery automation anytime commits land in your associated repo. This is great for iterating on solutions post-commit, but as a developer, I actually want to get feedback before I make my commits. Here's some examples of how OpenShift helps fulfill that use case as well. OpenShift provides centralized logging and metrics via Elastic, ElkStack, and Prometheus. You also have easy access to terminals using kubectl exec or OC exec. Once connected, you can use kubedns to contact Kubernetes services by name. This example shows using curl to contact a Kubernetes service by service ID http-base. Environment variables are easy to add to deployment configs or other files using the OCENV shortcut. Here's the live development example I mentioned earlier. If I have a local clone of a repo and a remotely running pod defined by OC get pods in this example, I can use the OC rsync command in order to synchronize changes from my local repo into a remotely hosted container on the platform. This workflow allows me to preview changes before I commit by syncing content into the running container. Once I'm happy with my changes, I can then use git commit and git push in order to see the automation pipeline rebuild and redeploy in order to confirm whether my suspicions are correct, whether my testing looks good. OpenShift also helps you share and replicate your success. The service catalog and brokers are one solution that helps make this very easy. You can go to www.openservicebroker.api.org for more info on this topic. The left side of the screen shows a service catalog integrated into OpenShift with a variety of icons that can be used as starting points for developers. The right side of this diagram shows pluggable broker backend design by a variety of broker providers. One solution is the OpenShift template broker. This has been included in OpenShift throughout the most of the OpenShift 3 series. New features in OpenShift are the OpenShift automation broker or Ansible playbook broker. This allows generic system automation to be fired off with a click in the service catalog. An Amazon Web Service Broker is available for launching AWS services via a OpenShift Service Catalog front end. There's a collection of other service brokers available from additional service providers and platform providers as well. A lot of other folks like Cloud Foundry and IBM are also working on this mechanism for sharing and leasing services internal to enterprise organizations. You can use the template broker as an installer to onboard new web developers. For example, if I were to run OC create-f on a local template file, I can install the template into my current project scope, making it easy to reuse. I can also use OC create-f on a remote file in order to install it into my local project context. Here I've provided a multi-service application example bundled up as a template file. If you run OC create-f on this file, it should install it into your service catalog. You should then be able to click on the solution and deploy the bundle in order to basically deploy about 7 different web services altogether, or 7 different API resources. When you're done, you should be able to run OC get all to list all the resources that were created using this single web workflow. Hopefully this shows how it can be very easy for advanced developers or lead developers to work on these lower level Kubernetes abstractions and standardize the collection of what the more average web developers should be working on. Team leads would package these things up, make them as a template, install them in the catalog, and then average web developers could come through, select, I would like stack A, please, that has already bundled up everything they need in order to be productive without a assumption that they would need to learn what is a pod, what is a replication controller, what is a deployment, what is a registry, what is a route. Really all the average developer needs to know is what language they're working on, which stack to click on, and where their repo is located. And we should use standard Kubernetes resources in order to fulfill the request and provision a URL that they can use in order to contact their application. For more information on Kubernetes, you can check the official Kubernetes/Kubernetes repo on GitHub. This is where all the Kubernetes sources and official releases are maintained. Kubernetes docs are available at kubernetes.io/docs. You can also find official sources and releases for OpenShift at github.com/OpenShift/origin. OpenShift docs are available at https://docs.openshift.com. If you'd like more learning opportunities, feel free to download a free O'Reilly ebook, Deploying to OpenShift, at www.openshift.com/deploying-to-OpenShift. You can also go to learn.openshift.com for free access to Kubernetes and OpenShift learning materials available right in your browser. For more ways to try OpenShift, try OpenShift Origin or Minishift. Developers can try Red Hat Code-Ready workspaces for fully containerized development, including an IDE. OpenShift Online is an easy way to try OpenShift in a hosted manner using the starter or pro plans. OpenShift Dedicated is a way to have OpenShift operated by Red Hat and available on AWS, GCE, or Azure. OpenShift Container Platform is the most analogous to RHEL. It's supported by Red Hat, but administered by you. And we would expect RHEL and or CoreOS as the host OS on those machines in order to protect the host from being compromised and provide the multi-tenant security that OpenShift provides. To take a look at our latest work, you can go to the OpenShift 4 developer preview at try.openshift.com. This includes all the latest and greatest features from the CoreOS technology line folded into OpenShift in a new major V4 release. I'm definitely looking forward to seeing what's new along this project. So keep an eye out for try.openshift.com. Thank you very much for sticking around. This has been Introducing Red Hat OpenShift 4, Part 1, an Introduction to Kubernetes. I'm Ryan Jarvinen, or Ryan J. Tune in next time for Part 2 in this series. We'll be talking about operators and platform automation. See you next time.